condition number 3. Okay. So now, based on distortion energy, right? So I'm going to introduce you to his formula now. Okay. So is UD is equal to 1 over 6G. I'm not going to derive it, okay, but we're just going to take this formula, okay, we're just going to apply this formula, where we have our stress A squared minus by stress A, stress B, right, plus by stress B squared, okay. So this is von Missy's formula, the expression of his criteria. So I'm still going to label this equation number 1. Okay, so where UD corresponds to the distortion energy. Okay. Okay, distortion energy. Now, so what is stress A, stress B, so on, and so forth. So where stress A and stress B are the principal stresses, okay, and G is termed the modulus of rigidity. Okay, G is termed our modulus of rigidity. So probably you guys have seen G before. So there's a formula. So I'll write the formula for you guys. So where the formula, one, okay, where we have shear stress is equal to G gamma. Okay, where this is correspond to shear stress tau alpha or gamma is shear strain. Okay, so this is Pascal, this is unitless, and G is the modulus of rigidity. Okay, and then now this formula is similar to, it's basically Hooke's law, right? So this is under shear. If normal stress, you have this, right? Right, where sigma tau is your normal stress, okay, and epsilon is your normal strain, okay, where E is your Young's modulus of elasticity. Okay, so again, this is in Pascal also. Okay. Right. Okay. So from equation 1, so let's look at equation 1. Okay, so I'm going to, so from equation 1, okay, so I'll write up equation 1, don't worry. So from equation 1, right, we're going to let stress A is equal to stress U, okay, and stress B is equal to 0, okay. So where stress Y is the U strength, okay. So we're going to put everything, all this into equation 1, okay. So if so substitute, okay, into equation 1, okay, not from, okay, so we're going to let, okay, so this is just one condition, okay. So we have U D. Now we're going to do until yield, okay. So this will be equal to 1 over 6G, right? So then stress A squared minus by stress A multiplied by B stress B plus by stress B squared, okay. So I'm going to copy the formula, okay, and put it over here. We just applied this formula, okay, nothing complex. Right, so this is our equation 1, right? So when that's the case, what we have is equal to stress U squared divided by 6G, okay, and this is known as von Mises criteria, okay, that is known as von Mises criteria. So how are we going to apply this? Okay, so the structure is safe. Okay, the structure is safe when, right, the distortion energy, right, is less than the distortion energy at yielding. Okay, so over here, this is acquired from material property, mechanical property, and the UD over here is from structure analysis. Okay, so this is basically from materials handbook. Okay, okay, right. So if we were to equate the both equation, right, so UD, we know there is 1 over 6G, right, stress A squared minus by stress A stress B, right, plus by stress B squared, right, and this thing has to be less than 1 over 6G, right, stress U squared. Okay, so now if we were to, we can get rid of 1 over 6G, we can normalize them, you can get rid of this, so that expression, okay, so I'm going to call this equation number 2. So equation number 2 becomes stress A squared minus by stress A stress B plus by stress B squared must be less than stress U squared. Okay, right? So now I want to introduce you to a to a parent function. Okay, I'm going to introduce you to a parent function. Okay. So the parent function that I'm going to introduce to you. Okay, I'll tell you what I'm going to do. This parent. Once we have this parent function, then we can map out the operating region of Tresca's criteria. Okay, so the parent function. Let's look at a parent function of the ellipse equation. Okay, so if you look at a parent function of an ellipse equation, you have x squared over a squared plus by y squared. Probably you guys have seen this in high school or in your math course. Is equal to 1. Okay, so you make them a common denominator. B squared x squared plus by a squared y squared is equal to 1 over a squared b squared. Right? Then you get rid of the denominator. Right? Then you have you bring it across, so you have b squared x squared, right, minus by a squared b squared plus by a squared y squared. The whole thing will be equal to 0. Okay, so somehow this parent function that we've just derived is a parent function of a ellipse. Yes or no? Right? So now if we're going to force this, right, parent function into this, so there are identical features over here. You can see here, right? Right, they are identical features that you can see there, right? Okay, so now we can superimpose a map, right, based on what we have drawn with Tresca before. Okay, so let me elaborate what do I mean. Okay, so now if we go into, right, so this is our axis again. So this is our stress A. Then we have our stress B, right? And then we have our yield again. Okay, so for Tresca, this is the operating limits. And so you guys have seen this before. Right, so this is for, yeah, put down here. This is for Tresca, right? Whereas for Mises, because the parent function, right, is similar to the ellipse equation, right? You have b squared x squared minus a squared b squared plus y a squared y squared. Now you have what? Stress a squared minus stress a stress b plus y stress b squared, right? So when you plot this, right? So if you were to ask me, yeah, so if you were to plot this over here, right? Because it's a ellipse function, okay? So I'm going to sketch an ellipse now. Okay, I'm going to sketch this, okay? Okay, so the one in pink, this is Vomicis criteria.